Set operations are fundamental to working with sets, much the same way that addition, subtraction, multiplication, and division are fundamental to working with arithmetic. So we want to begin with demonstrating 5 of the basic operations with sets, and to do that we'll use this universal set here, 1, 2, 3, 4, 5, 6, 7, 8, and then within that the two sets A and B. A is 1, 2, 4, and 6. Those are the 4 elements in A, and then the 4 elements in B are 3, 4, 5, and 7. The first operation we want to look at is what's called the union. The union of two sets, A union B, it's like a horseshoe symbol. And when you think about union, you're bringing everything together, combining all of the parts of A with all of the parts of B. So as long as an element is a part of A or a part of B, then it would be included in the union. And so in this case, you can see that 1, 2, 4, and 6 come from A, 3, 4, 5, and 7 come from B. Put those all together in the union, and that's about as simple as it gets. The union includes everything, just putting it all together in one large group, like a workers' union, United Auto Workers, or similar to a union of the European nations, all coming together. One of the tools that we use when working with sets is called the Venn diagram. Venn is a French mathematician. He came up with this way of representing sets using rectangles and circles. The larger rectangle on the outside is representative of the universal set, and then everything within the universal set shows up in the rectangle. And so you have set A and set B. The subsets of the universal set, those are represented with the circles. And in this case, we'll draw the two circles with an overlap just in case they have an element in common. And sure enough, in this case they do. You can see that both sets have a 4. And so in this case, 1, 2, 4, 6, 1, 2, 4, 6, 3, 4, 5, 7, 3, 4, 5, 7. That represents the relationship between the two sets. And then 8 is a part of the universal set, but not a part of either one of the sets, so we put that out here. Now, to represent union, union includes any element that's a part of A or a part of B, so all of that. So this part that's shaded inside indicates the region represented by the union of A and B. That's pretty typical of what a union looks like. You just shade all of the parts. The second operation we want to look at is what's called the intersection, where two lines where two lines intersect. They intersect at a point, and that point is a part of both lines. When you stand in the intersection of two roads, you're standing on both roads. The intersection is a collection of all of those elements of A that are also elements of B. So an element of the intersection is going to be an element of A and an element of B, having to meet both requirements. And you probably can guess already that we've identified this up top here as 4. When we shade for the intersection, we would shade only that region of the Venn diagram that's a part of both sets, both B and A. And so that would be this portion right here. Another technique for shading intersections that I want to make you aware of at this point, it'll come in handy later on when we work with slightly more complicated operation pattern and using a different pattern for shade A in one direction and then shade B in the other direction. The intersection is that region that has both patterns, because again the intersection is those elements that are a part of A and a part of B. So when you are shading for the intersection, look for the region that satisfies both conditions. Okay, first two operations, union and intersection. The second page here will talk about some of these other operations. The third one is the symmetric difference. The symbol for that is a triangle, similar to the delta that we use in calculus. We're talking about the change. Just to recap, the example that we're working with is the universal set 1, 2, 3, 4, 5, 6, 7, 8. And A is 1, 2, 4, 6, B is 3, 4, 5, 7. And so when we talk about the symmetric difference, one of the ways to think about that is to recall when you're working with logic, the exclusive or. The exclusive or, we were talking about bringing together, you know, it's like an or statement, but one or the other, but not both. That exclusive part, but not both. That applies with the symmetric difference, because with the symmetric difference, you're looking for those elements that are a part of the union, but not in the intersection. So they're an element of A or B, but not in the overlapping region. So in this case, if you remember, the union was 1, 2, 3, 4, 5, 6, 7, but now the symmetric difference does not include 4, because 4 is in the intersection. So it's the union without the intersection. Now your book will talk about this a little more detail, but I think this is going to give you a pretty good overview. If we shade this with a Venn diagram, again, this looks very similar to the union, but you'll notice that we've left out this overlapping region. We've left out the intersection. So the symmetric difference is how are they different, not what do they have in common. Okay? And similar to the exclusive or, remember, we talked about if it's one or the other, but not both. So symmetric difference, that's our third operation. The fourth one is pretty simple. It's called the complement. This is an example of what we call a unary operator. It can operate on just one set, and not too different from the negation that we saw back with logic. When you see the complement of A, the symbol is the line above that, above the A, so that's the complement of A, or another way to think of that is not in A. And so when we're looking for all of those elements that are not in A, within the universal set, what are the elements not in A? Well, you might think, well, that must be B. Well, no, it's not just B, because that includes some of A, but it also includes those elements that are outside of B. So when we say not in A, 8. Okay?
And when we're shading for a complement, we're just leaving everything blank that's inside of A, and we're shading only the region outside. Okay? So you can see that we don't include this portion of B because that's in A. So everything that's not in A is what we mean by the complement of A. You can also use the complement with a combination of operations. So here we're taking the complement of A intersect B. Now you remember on the previous page we've already seen that the intersection of A and B is 4. So when we are shading for, or when we're trying to identify the complement of the intersection, what we're looking at is everything that's not in the intersection. Again, similar to what we looked at with logic. So everything that's not in the intersection, everything that's not in this overlapping region here. So all of the stuff out here, and you'll remember that's 1, 2, 3, 5, 6, 7, and 8 as well. Okay, now look at the difference here. Everything that's not in the intersection, 1, 2, 3, 5, 6, 7, 8, the symmetric difference of A and B is 1, 2, 3, 5, 6, 7. 8 is outside of the intersection, but 8 is not a part of the union
of A with B. So that's why 8 is not included in the symmetric difference, but it is included in the complement of the intersection. All right, union, intersection, symmetric difference, and complement. And finally, the last one we want to look at is just what's called the difference. The difference, and you might, as I mentioned before, some of these might remind you of some of the operations out of arithmetic. The difference is not all that different from subtraction. A fancy way to talk about the difference is given in your book, and they refer to it as the relative complement of B in A. Remember, we just finished talking about complement. So the complement of B is everything not in B, but it's more than just the complement of B. It's the complement of B that's still in A. So everything outside of B that's still in A. Elements of A that are not also elements of B. If you think about it, if we started out with set A and we removed B, then we're looking for all the elements that are in A, but also not in B. Here, with our example, we had 1, 2, 4, and 6 are in A, 3, 4, 5, and 7 are in B. If we were to remove 3, 4, 5, and 7, how would that affect A? Well, 4 is a part of both, so 4 would be removed if we were to take B out of it. You can think of it this way: if these are the 4 math majors and these are 4 computer science majors, and the computer science majors went on a field trip, well, we're going to lose a math major to that field trip. Okay? So by removing B, that affects A because 4 is in the intersection. And we'll revisit this when we look at some other properties of sets, but basically we're removing B and seeing what remains of A after we do that. If we shade this, this is elements of A that are not also in B. So this is all the elements in A that are not also in B. So just this portion of A out here. And there you have it. Those are the 5 basic operations when working with sets.